another module in this massive open online course on probability and random variables for wireless communications. So, we are looking at independence, the concept of independence and independent events, and let us look at one final example to understand it. We have already looked at several examples in this context to better understand the concept of independence and more importantly its relevance in the context of wireless communications. Remember, in the beginning of this course itself and in the introductory module also we have said that this is not simply an abstract course on probability and random variables. This is not a course in simply the mathematics of probability and random variables. One of the important aspects of this course is to explore and examine the impact or examine the relevance of probability and random variables, random process in the context of communications, especially digital communication systems and modern wireless communication systems, so that it bridges or basically builds a bridge between these abstract concepts in probability and random variables and the practical applications of these concepts in the context of modern communication systems, both high speed digital communication systems as well as high speed wireless communication systems, 3G and 4G wireless communication systems. So in this module let us briefly at a very high level look at another very important impact or relevance of this concept of independence or independent events in a wireless communication system, and I draw this example from the context of 3G, 4G wireless communication systems. Some of you who have seen previous courses on wireless communication systems might have already seen this. This is a concept in the context of what is known as diversity, right. So, let us look at an example of independence in the context of wireless communication systems. So, I am looking at independence in the context of wireless systems, right, and especially in the context of 3G and 4G wireless communication systems. And what we would like to look at, what is known as the probability of a deep fade event. We would like to look at what is known as the probability of a deep fade event. Some of you might already be familiar with this concept of a deep fade, but if you are not familiar, let me explain this to you briefly at a high level. The wireless communication signal that is received at the receiver in a wireless communication system, it is a result of the superposition of multiple signal copies that arise, for instance, from the direct signal that is coming from the base station, or also multiple copies that are coming from the reflections from various buildings, various trees and other objects in the wireless environment. So, when these signals superpose at the receiver, there is interference, and this interference can be either constructive in nature or it can be destructive, which causes fading. So, the interference in the wireless communication environment that results in fading, right, that is which is basically either an amplification of the received signal power or the dip in the received signal power. This process is known as fading. And when the received signal power dips significantly below a certain threshold, that is below a certain threshold and below the noise threshold at the receiver, so that communication is not possible, that is known as a deep fade event. So, a deep fade event, to put it simply, that is a significant, let me put it simply, this is a significant drop in the received signal power in a fading wireless channel. So, the significant dip in the received power in a fading wireless channel or in a fading wireless system, this is known as a deep fade event. Obviously, we would like to avoid a deep fade event, because whenever the signal is in a deep fade, then communication is not possible between the transmitter and receiver, because simply the received signal power is very low. And one way to avoid a deep fade is through what is known as multiple antennas. By increasing the number of antennas at the transmitter and receiver, one can significantly reduce the probability of deep fade. Let us look at how this happens. So, let us say I have a transmitter which is, let us say, something like my base station. So, let us say I have my transmitter, I have my receiver. Let us say my transmitter has a single antenna, but my receiver, let us say, has multiple antennas. So, my receiver has antennas 1, 2 up to L antenna. So, these are multiple antennas at the receiver. These are L antennas. I have a single antenna at transmitter, although in the most general case one can have multiple antennas both at the transmitter and the receiver. For the purpose of this simple example, we are looking at a single antenna at the transmitter and multiple antennas, L antennas at the receiver. This is known as a CMOS system. This is a single input multiple output system, because I have a single antenna at the transmitter, that is the input, multiple antennas at the receiver, that is the output. This is known as a CMOS system, or a single input multiple output system. So, this is known as a SIMO system, where a SIMO stands for single input single input multiple output, and therefore, in this system we have L links, we have 1, 2 up to L links. So, we have link 1, 2 up to L links. What do I mean by L links? We have a link between the transmit antenna and each receive antenna, right. So, in this system what we are saying is we have basically L different links, because I have a single transmit antenna and L receive antennas. One can consider the one can consider the channel between the single transmit antenna and each of the receive antennas as a link. So, we have single transmit antenna, L receive antenna. So, there are L links in this system, and now therefore, the probability that each, now let EI, let this denote link I is in deep fade. What we are saying is, let EI denote the event, let this quantity EI, let this denote the event that link I is in deep fade. So, each of these links can be in a deep fade, that is, the SNR received at over this link is below a certain threshold or below the noise threshold, and we can say that then the link I is in deep fade, and let this EI denote the event that link I is in deep fade. Now, therefore, one can ask the question, when is this wireless communication system, when is the whole system is in a deep fade? The whole system is in a deep fade, that is, no communication is possible naturally if all the links are in a deep fade. In this system with L links, the communication between the transmitter and receiver is not possible if all these links, that is, each of these L links is in a deep fade. So, the system, the entire wireless system. So, basically the system is in a deep fade if all the links are in, if all the links are in, if all the links, if all the links, the system, the wireless communications is multiple antenna wireless communication system is in a deep fade, if all the links are in a deep fade. Now the probability that each of these individual links is in a deep fade is equal to 1 over SNR. This is a result from wireless communication which I am not deriving here. This, the probability that each of these links, the probability that link EI, the probability of this event I, the probability of this event EI that link I is in deep fade is 1 over SNR, right, which is basically 1 over P over sigma square, where P is the transmit power and sigma square is the noise power at the receiver. So this P, so let me also clarify this, P equals the transmit power and sigma square equals noise power. P over sigma square is the SNR, and the probability that link EI, the probability of EI, that is the event that link I is in deep fade, is 1 over SNR, and we are asking the question, what is the probability that the entire system is in deep fade? That is probability of deep fade of the system is basically, we said, the probability that all the links are in deep fade, which is the probability that E1 intersection E2 intersection E3 so on and so forth intersection EL, that is the probability of the joint event. Therefore, the probability that the system is in deep fade is the probability that all the links are in deep fade. Now I am going to use the independent assumption to write this as the probability of E1 times the probability of E2 times the probability of EL, and this is a key. This is using assuming all links are fading, assuming all the links are fading. So what we are saying is the probability that the system is in fade is the joint event, that is E1 intersection E2 so on intersection EL, that is the joint event that all the links are in a deep fade, and the probability of this joint event we are saying is the product of the individual deep fade events, that is the probability of E1 times the probability of E2 times so on the probability of EL, given that all of the links are fading independently. And previously we had seen that the probability that each of the links, each of the individual links is in a deep fade is 1 over SNR. Therefore, the probability of this joint event is basically simply given as 1 over SNR times 1 over SNR times 1 over SNR, which is equal to 1 over SNR raised to the power of L. Therefore, the probability of deep fade, if I call this as PDF, this is equal to 1 over SNR raised to the power of L, and this is an important property in wireless communication systems, especially in modern 3G, 4G wireless communication systems. This PDF, this is the probability of deep fade, this is the probability of deep fade, which is basically 1 over SNR raised to the power of L. So, we are saying that as the number of antennas, at the receiver increases, the probability of deep fade, that is the probability that the system is in a deep fade or the signal power at the receiver is below the noise threshold, decreases as 1 over SNR raised to the power of L, and therefore, having a larger number of antennas helps improve the efficiency of communication, or helps decrease the error rate, helps decrease the bit error rate of communication, because the probability of deep fade decreases, as we are seeing in this. We are employing the assumption of independently fading channels. This property is known as diversity. The probability where the probability of deep fade is decreasing as 1 over SNR raised to the power of L, this is known as diversity. And this leads to diversity leads to a significant decrease in what is the bit error rate or the BER of wireless communication. So, what we are saying is, having multiple antennas, the probability that the system is in a deep fade decreases as 1 over SNR raised to the power of L. So, the larger the number of receive antennas, the probability of deep fade becomes correspondingly lower, and therefore, this leads to a significant decrease in the probability of deep fade, which in turn leads to a significant decrease in the bit error rate of wireless communication. This is an important property in 3G and 4G wireless communication systems, where you employ multiple antennas at both the base station, either the base station or the handset, and if possible both at the base station and also the handset. The main reason is because having multiple antennas leads to a significant improvement in the reliability of wireless communication. This is achieved through the property of principle of diversity, and the principle of diversity fundamentally is based on the assumption of these independently fading links. So, this is a key impact or a key relevance of the concept of independence and independent events in the context of wireless communication, especially modern 3G, 4G wireless communication systems. So, with this, let us stop this module here, and I hope I have explained an important aspect of independence in the context of wireless communications. Thank you very much.